The 555 timer, that's the basic block generating signals that will be useful to other integrated circuits, digital integrated circuits. The reason is that the integrated circuits have functions that rely on changes of voltage levels. Sometimes there are tasks that will happen, that will be permitted to happen, that will be designed to happen based on the fact that some signal is either high or low. That's when we have level control. But in some cases, in many cases, in fact most cases, it may be related to a transition. When the signal goes from high to low, at the moment it goes from high to low, or at the moment it goes from low to high, other integrated circuits may respond by having some transformation in signals or behavior or status of the outputs of those ICs. So the idea, therefore, is to have our own signal, our own clock signal, our own controlling signal generated on the board, which would be useful for one of the experiments, the one that is related to the 8 LEDs that light up one at a time, and also will be necessary for the final project, which is related to the traffic light controller. So if you look at a diagram of the 555 timer, this is only one configuration that is possible, and this one specifically was designed so that the signal will go from high to low at a specific rate. That rate will depend on the external components, and in this case most predominantly R2 and C2. You see, this is the IC, the 555, and around which we have provided other components so that the signal that will be generated will be, first of all, according to this expression here, assuming that R2 is at least 10 times larger than R1, which will make R1 negligible in the calculations, then the period will be approximately equal to 1.4 R2C2. It is obvious that in your case that C2 may be a fixed value. The reason is that you may not have a lot of choices in terms of capacitors in your kit, but you have a lot of choices in terms of resistors. Therefore, it is advisable to obtain that capacitor, which in this case is 100 microfarad, and establish based on what is required. In this case, we wish to have a period of 1 second. See what R2 would be equal to so that the 1 second will be obtained. It's obvious that for this demonstration, I chose about 1K for R1, which is about 10 times smaller, but the 10K in the 100 microfarad will make it a little bit different than a second, but it will suit our purpose because it's going to be slow enough for us to see that the signal changes from high to low and for us to verify it visually, that is with our own eyes. In addition, we have, as far as the verification process, an LED which in series connected with a resistor, possibly 220. In the demonstration, probably I'll use 100 ohm, as you were told before. Anything between 100 ohms and 470 will do. Any higher, the brightness may not be that great. Any lower, it may not limit the current as well. And so we just want to make sure that we have an idea of the output and without having to use a meter or the probe. Now the signal, if you look at the signal here, it has been generated under simulation purposes, and you see here that the signal at the output of the timer changes from high to low without any other controlling signal. As soon as the circuit is powered up, it starts generating the signal, right? 0 to 5 volt. This is the kind of signal that we will be needing for other ICs to perform their operations. In addition, the fact that R2 was much larger than R1 made it such that if you look at the period, which is the time beyond which it just repeats itself, you see here that the signal repeats itself. This is the time where it is high or on. This is the time where it is off. And you see that time period is equal to this time period, which tells us that the on time is 50% of the whole period, and that's what we call 50% duty cycle. At this point, of course, it doesn't really matter, but it is something good for you to know, because in the future that duty cycle may become an important parameter in the design of the circuits. So, the first thing that we're going to do about the demonstration is to teach you how to implement a circuit by shortening the time it takes to have a working one. Even though when bugs occur, it is good because you get to learn a lot from debugging a circuit. You learn a lot from the behavior, the effect of some components on the circuit. But what is important also is to be able to do the experiment within a given period of time, and to be able to have a working circuit within also, even for design purposes, within a short period of time. So the first thing that I have about the board is that I want to make sure that the power is available, and is available in an efficient way, in a convenient way. You see here that, and I have told you before to do it for the proto boards that you have available, that I have connected the upper row to the upper row of these row strips, and the same thing with the bottom one, using red for power, black for ground, using the short circuits between these two half strips, because in this specific board, the two halves are independent from each other, and this is something that remains there. In fact, you may extend it to another strip, because the final project may require more than than one strip to be used. And so it makes the power and the ground available on all these row strips. And the reason is that if I want to connect the bottom pin to ground, I don't want to have a wire jumping over components, because as you cover some of the components and you have to remove them to replace them, you may have trouble where you may lose some of the connections. And so it will be a good idea to avoid any wires over any of the components. On top of that, I'm going to show you here how to minimize the number of wires as much as you can. So you see here that the 555 timer, and I'm going to connect the components as I see them in the circuit. And of course, in your case, you may want to work as a team, where one student will tell you what to connect, and another student does the connection, and a third one will investigate as you're doing it that the connections are made adequately. And so, in this case, what we're going to start with is we're going to be looking at some of the connections, some of the pins, and we will see, or you will see through the circuit, or if you remember from the circuit as you have the manual facing you, that pin number 8 and pin number 4 are in this case connected to power. You see pin number 8 and pin number 4 are both connected to 5 volts. And so those are the ones that I'm going to start with. And so pin number 8 is here, right? The top left is here, and even though this wire is not short, I'm going to put myself in your condition, where maybe I don't have a trimmer, maybe I don't have a cutter, maybe I don't have a pair of pliers, and so I may use whatever I can, but it would be a good idea to have a set like that you carry all the time when you come to the lab. And so I need a second line for pin number 4, and as you see here, had this wire been shorter, it would have been a better connection. And I'm not going to send it here, jumping over components. I'm going to send it to the bottom row, where I have said before that the connection to power would make it useful. And so I try to avoid jumping over components. The second element here is pin number 1, which goes to ground. So I'm going to start with pin number 1, using the bottom one, because I want to keep the other holes available for the other components. And so I'm going to connect it to ground with the smallest amount of being an obstacle to other components when I need to connect them. And now what I'm going to do is I'm going to look at the components, and I start with the ones that I can handle, the ones that are simple, the ones for which the connections are straightforward. For example, the 0.1 microfarad, which is this capacitor here. In fact, in this one, it's written directly on top that it is 0.1. If you are in doubt, you have an RLC meter, which allows you to measure capacitors or the capacitance of the capacitors, and so you can verify. And in this case, this capacitor goes from pin number 5 to ground. So pin number 5 is here, and the ground is here, and I'm going to send it to ground without the usage of extra wires. Right? The less wires I have, the easier it is to debug, and the easier to check when things don't work well. And also the less, the more reliable the circuit is, because the less elements that can go wrong. The next one is the larger capacitor, which is the 100 microfarad. And I told you for calculation purposes, C2 is 100 microfarad because that's the only one you have in your kit. So you don't have a choice. The only one you can play with is the resistor. And so you see that this electrolytic capacitor has one terminal which is marked with minus. Usually it may be important to connect that terminal to the lower potential. And so we're going to be learning to be careful. And what we're going to do is, since C2 is connected from pin 6 or pin 2 to ground, as you see here, you see this point here is connected to either pin 6 or pin 2. So it's obvious that either one will do. And so what I'm going to do, most likely, I'm going to use pin 2 and connect my capacitor, the negative side of it, to ground. And so this is pin 2. And the other side would be connected to ground, which I'm going to use the bottom strip for, right? And this is my connection. Since we have seen right now that pin 6 and pin 2 are connected to each other, I'm going to use a wire that will go from pin 6 to pin 2 and provide me with the connection. However, as you see, it jumps over, so I'm going to lay it down so that I can have access to the IC if there is a need to change it. After that, the next component that I think of is R2, which is 10 kilo ohm, and the 10 kilo ohm is here. This is 1K, so this is 10, and 10 kilo ohm is between pin 6 and pin 7. It could be pin 2, pin 7, but I choose to use pin 6 and pin 7, but because they are close to each other. And so as I connect the resistor there, you see here I can make that connection without using any wires whatsoever, right? The less wires, the better. Then on top of that, a 1 kilo ohm resistor, which is connected from pin 7 specifically to power. To pin 8, because power is pin 8 at the same time. So I can connect it to the power line, or I can connect it to pin 8, whichever is better for me. And it's obvious that if I connect it to power, it will be better for me because they're closer and therefore more space available anywhere else for other components to be connected. And so now I have connected, you have to have good eyes to make sure that it is inserted in the right columns. And so now I have the 1K between pin 7 and pin 8 or power, which is the same thing. So we have connected our 4 components, and now it is our turn to check the status of the output. But before we do that, if you look at this circuit that I built here, a very simple one, which is from the anode, from power to the anode of the LED, and from the cathode to a 100 ohm resistor back to ground. This is just to show whether the power exists, whether the LED itself works, and so if it lights up in this direction, we know that the LED is working properly, and there is at least a 5-volt power, which I can see here. And hence, knowing that I verified that I have power, since I don't have a meter or probe, so now I'm going to be connecting that LED and that resistor to the output of the timer, which happens to be pin 3, and so it will give me the ability to verify the working condition or the working status of the timer. And so now I'm going to connect my LED anywhere here. Of course, I'm going to use as little space as possible. In fact, I would get it even closer if I could, because when it comes to the final project, you're going to have a hard time when your components are all spread all over the power board, because the wires will be so long and there'll be so many, it'll be like a jungle, and you will not be able to guarantee that if the circuit doesn't work, that you'll be able to debug it. And so beyond the cathode, and then after that I go to the ground again, and this will give me the possibility for the LED to turn on when the output is high, to turn off when the output is low. And so as it blinks, hopefully at the rate of something close to, it's not going to be exactly 1 second, because if you evaluate the period with 1.4, R2 equal 10K and C2 equal 100 microfarad, that's going to be a little bit more than about 1.4 seconds or so. And so, but for the purpose of the demonstration, it will be good enough for the purpose of even other circuitry. And so if you want to play with the resistor R2, change the value of it to try to get 1 second, or we may be satisfied with something close enough. And so if you look as I power up the board, the circuit, hopefully it will blink at the rate that is assigned, which is 1,000, 2,000, 3,000, which is close enough, right? But at least the blinking here shows you that the signal at the output of the timer goes high, low, high, low, high, low, and we can almost feel that it takes as much time for the high to occur as for the low, which is the 50% duty cycle that I mentioned before. And we will see other circuits in the future.